our speaker today is the let's see, where's my Dr. Dr. Zhenbin He from MIT, and currently a senior research fellow with the Sensible City Lab at MIT. And before joining MIT, he worked as a full professor at the Beijing University of Technology in China. So Dr. He's research interests include traffic flow theory, urban mobility, and sustainable transportation. He has published a large number of academic papers, more than 140, and recently he was listed as the world's top 2% scientist by Stanford University. He's also served on the professional organizations, for example, an associate editor for the IEEE TITS, and also as an editorial advisory board member for emerging technologies. So I also want to acknowledge that Dr. He, as well as Dr. Yang Zhou, and also Professor Jorge Lava that we had in last couple of weeks, were all invited by our new faculty member, Dr. Hao Zhou. So he also, helped facilitated the communication, also the trips of our speakers. Unfortunately, Dr. He couldn't be with us today in person. There's some weird rules about covering the guest speakers' hotel nights. So it caused some challenges for Dr. He to travel to Tampa. But we hope next time we could have him with us and then, meet with our faculty members and friends. So given that we have already been late, I'll just give the floor to Dr. He and look forward to your presentation.
Okay, thank you, Dr. Zhang, for introduction. And okay, let's present. Okay, and good afternoon, my friends. I'm happy to participate in the Friday Transportation Seminar series at University of South Florida and introduce my latest research on beautifying traffic while enhancing time-space traffic diagrams. My name is Zhengbin He, and I'm a senior researcher right now at MIT Sensible City Lab. Okay, let's directly go to the content today. The time-space diagram is one of the most important transportation visualization and analysis tools. Is in the time-space diagram, x-axis is time, and y-axis is space, and the colors represent traffic states. Usually it is speed, and we can easily find a lot of time-space diagram in research paper, and almost all traffic data center and display platform employ time-space diagram to visualize traffic dynamics. Okay, and from a time-space diagram, we can identify traffic bottleneck, understand traffic characteristics, predict travel time, and even estimate traffic emission. Okay. And however, when we zoom in the diagram, we will see it usually shows teeth shape, which is obviously incongruous with real world traffic and looks ugly. In other words, the time-space diagram itself is with a lot of errors. Okay, generally speaking, the errors come from the way that we construct a time-space diagram. I present to construct a time-space diagram, we virtually partition a time-space plane into homogeneous cells and then fill the cells with colors that are determined based on the traffic states of the cells. So one of the causes is the fact that time-space cells are usually too large, making traffic detail erased. Another cause is the currently used rectangular cells cannot incorporate the propagation direction of traffic waves. So, aiming at the cause one, we introduced the time-space diagram refinement problem and solved it with a multiple linear regression model. I'm going to introduce the work in the following slides. Okay, Here, the refinement of a time-space diagram is all about enhancing image resolution. In computer science, it's referred as super resolution, which is an active field, particularly with the development of deep learning approaches like CNN. However, there are two drawbacks for those deep learning-based super resolution approaches. One is the computational cost is high. The other is training a model needs a large number of high fidelity image data. For the traffic space diagram refinement problem, the second drawback matters. That is, it's difficult to collect a large number of high fidelity, large time-space scale traffic data, which costs a lot. So we define the time-space diagram refinement problem in the work as follows. Given the time-space diagram, partition each cell into 4 homogeneous subcells and estimate the traffic speed of 4 subcells to achieve the goal of refining the time-space diagram by enhancing its resolution. To solve the problem, we proposed a two-step method. Given a time-space diagram, step one, we determine the traffic condition of each cell according to a threshold of traffic speed. Step two, for each subcell, we estimate its speed by fitting the following multilinear regression model, where xi is ground truth speed and of cell I and its surrounding cells. pkj is the regression coefficient. There are 4 subcells for each cell, so we got 4 regression models in total. Okay, and the data for model fitting was collected in 2017 on a 2-lane freeway segment in Japan. The length of a segment is 2 kilometers and the total duration of data collection is 5 hours. The first hour of data is used to estimate the model parameters in this work. It can be seen from the right-hand side figures that the 1-hour data contain both freeway and congested traffic with typical traffic characteristics such as stop-and-go waves. And the maximum speed in lane 2 is slightly higher than that in lane 1. Okay, we only take 2 groups of cell size as example to present the results and do further tests. One of the group of settings is more consistent with the time-space distribution of data collected by real-world loop detector. And the fitting results are surprisingly ideal. All R squares are larger than 0.7, and most of R squares are even higher than 0.9. So validation, we employ 3 datasets to validate the proposed simple model. This is the data collected from different time, and this was collected at different location, and this was even collected in different countries. Okay, it's believed that such diversity of datasets could well guarantee the reliability of the evaluation and the transferability of the proposed model. Moreover, we do 2 tests. The first test is called 1-to-4 test. That is, given a time-space cell, we estimate the traffic speed of its 4 homogeneous subcells so that the resolution of the corresponding time-space diagram is increased 4 times. The second test is stricter. That's on the basis of 1-4 test results, we further estimate the traffic speed of the homogeneous 4 subcells of each of the subcells by using the estimated speed of those subcells. Okay, it's very glad to see that the results for all cells and the two tests are quite ideal because both the MAE and MAPE are quite small. And to give a more direct presentation, we plot one of the estimation results. And first, this is the high fidelity trajectory data used to construct time-space diagram. And second, we construct 3 time-space diagrams with different resolution and take them as ground truth. Then we conduct the 1-to-4 test and 1-4-16 test, respectively. Through comparison, we could see that the refined diagrams are quite similar to the ground truth, and no matter for 1-to-4 test or 1-4-16 test. Okay. And for more detailed analysis, error analysis indicates that the more detailed error analysis indicates that the proposed model will not result in large bias in refining some specific traffic states, including the boundary between the free flow and congested traffic condition. And it is curious to know if traditional traffic state estimation methods are competent in refining time-space diagrams, although a comparative method was proposed directly for the refinement problem might not be found at present. To this end, we select the classic adaptive smoothing method to make a comparison. It can be seen that the MAPE's results from the proposed refinement model are much smaller than those from the ASM. It's not difficult to understand that the ASM, which is based on a continuous filter, tend to generate smoothing results, making a time-space diagram looks quite foggy. Therefore, based on the above comparison, we may conclude that the proposed model outperforms the ASM when refining a time-space diagram. Okay, and then discussion, we have several things to say. And the first is in the proposed model, there's only one additional parameter, that is the speed threshold of distinguishing free flow and congested traffic condition. We conducted a sensitivity analysis which shows that its value do not significantly change the refinement accuracy. Turns out that the proposed model is not sensitive to the value of the parameters. Okay, second, we would like to say distinguishing free flow and congested traffic condition is indispensable. In the preliminary stage of the study, we did not distinguish the conditions and failed to capture the forward waves in free flow traffic. That is, we do not observe free flow waves toward to the top right corner. And third, about the transferability, we would like to say that good transferability has been demonstrated in the test with data collected at different time in different locations and even in different countries. But second, diverse and abundant traffic patterns has been involved in the evaluations. So at last, beyond adding new tests, good transferability could be actually guaranteed by the traffic characteristic itself. It's well known that traffic flow shows similar characteristics worldwide. Many existing works have achieved satisfactory estimation by simply input typical traffic characteristics. Okay, and regarding more discussions such as the simpleness of the method and feasibility of describing nonlinear traffic using linear method and the multi-collinearity regression and the computational cost. Please see the paper. Okay. Due to the time limitation, I will not introduce more details. Okay. And then, as I previously mentioned, another cause of inaccurate time-space diagram is the fact that current rectangular way of constructing time-space diagram doesn't consider wave speed, okay, which is a key feature of traffic flow. And to fill the gap, we propose a new way of constructing time-space diagram, which is based on non-rectangular parallelogram instead of the traditional way that is based on rectangular parallelogram. Okay. According to Eddy's general definition, only when homogeneous traffic states are contained by cells and the resulting average traffic variables are stationary and able to reflect the fundamental relations among speed, flow, and density. Therefore, so when constructing the time-space diagram, it's important to make the traffic states contained by each cell as homogeneous as possible. And traditionally, homogeneous RP, the RP stands for the rectangular parallelogram, okay, and are used to construct a time-space diagram. Well, we intuitively conjecture that using NRP stand for non-rectangular parallelogram cells performs better. And compare those two diagrams, it can be seen that in this case, at similar locations, NRP cells C and D in the right-hand side figure, okay? C and D contain similar completely process of deceleration and acceleration traffic. While in the left-hand side figure, the RP cells A and B do not. And generally speaking, NRP cells have more chances to contain complete stop-and-go process as well as homogeneous traffic. Although a stop-and-go process may not be completely captured by an NRP cell limited by each width, the traffic contained by the spatial neighbor NRP cells are more likely similar. It means that the NRP cells are beneficial to capture similar traffic waves. Okay, that's the logic behind the idea. And then we directly present the time-space diagrams constructed by using RP and NRP respectively. It's quite obvious that the NRP-based time-space diagram could, in the right-hand side, could reflect the wave propagation towards lower right corner, while the traditional one in the left-hand side is more like directly pointing down, it demonstrating that the advantage of NRP-based time-space diagram. And to quantitatively measure the compare the quality of time-space diagram, we extract travel time from a time-space diagram and compare the average travel time with the ground truth data. And subsequently, we did several tests to compare constructing time-space diagram using RP and NRP. One of the tests is under the condition given 100% traffic information. That is, we have complete trajectory data. Another test is under the condition given partial probe data. It's like the data collected by using floating cars. And we only have the sample data for certain vehicles and at certain time. The results in all the conditions show that the proposed NRP-based time-space construction outperformed the traditional RP-based method using the metric of average travel time. Okay, and moreover, moreover, we did a sensitive analysis of wave speed. It well known that wave speed is globally between negative 20 kilometer per hour and negative 10 kilometer per hour. Therefore, we make comparison using two wave speed at extreme conditions. Those are negative 20 kilometer per hour and negative 10 kilometer per hour. The results show that the NRP-based method is more sensitive to the sighting of wave speed and it still outperforms RP-based method. Okay, and by taking this opportunity, I would like to briefly introduce some of my work closely related to time-space diagrams. And the first two works is about congestion sensing, and they are solely based on floating car data. And this part of the work is aiming at freeway. And the purpose of the work is to avoid the difficulty of obtaining high fidelity digital maps and the time-consuming map matching. And then we proposed this mapping to cell method to sense traffic dynamics and freeway congestions. This is the big data mining method that fully utilizes the characteristics for traffic. The basic idea is we reconstructed the road network based on the floating car data. Like when you directly plot the floating car data onto a two-dimensional space plane, you could roughly see the road network. And based on those distribution of the floating car data, we reconstructed the road network using homogeneous cells. And then we reconstruct the road network using those homogeneous cells. And then we map those GPS data into the cells and then extract the traffic dynamic on those roads. And this is the basic idea of this work. And as a companion, we extend the mapping to cell idea to urban roads, but the proposed method could efficiently screen thousands of intersections and identify the turn level congestion to answer the frequently asked question in the city where there might be thousands of intersections and when and where that traffic congestion usually occur. Like right now, I ask you a question. Do you know in your city which intersection right now and at which turning direction it is congested? But practically it is quite difficult to answer. Okay, so in this work, we also partition the two-dimensional space into very small cells, but it's different from the previous work. The cells are much smaller, and then we reconstruct the intersection using those small cells, and then we map the GPS data into those small cells. That means we map the GPS data into the intersection, and then we can get the trajectory passing those intersections with turn at different turn directions. So based on this idea, we extract the traffic condition at turn level. Okay, and then this work, another work is we propose a mesoscopic carbon dioxide emission estimation model, and this model could estimate carbon dioxide emission directly from time-space diagram, and which better considers traffic dynamics. Right now, as we know, we have two basically traditionally we have two levels of traffic emission estimation model. One is macroscopic level, that is we gave link-based traffic speed, and then we got the emission at that time and on those links. Okay, that's the macroscopic, the macroscopic level carbon emission estimation model. And another level of model is macroscopic carbon dioxide emission estimation model that is vehicle based. That means we gave the acceleration and speed of a vehicle at a time, and then we get the emission at that moment. So that is macroscopic level carbon emission estimation, carbon dioxide emission estimation model. But this work is in between those two levels. That is, we call it mesoscopic because it is give more details data within the link, and in the model it consider the traffic dynamics. And we believe the model opened the gate for estimating carbon dioxide estimation for widely available low fidelity traffic data. Since the time-space diagram, which is the model input, can be constructed by using various traffic flow data, such as loop detector data and low-frequency floating car data. That means as long as you give me a time-space diagram, I could give you the corresponding carbon dioxide emission. And that means we have lower requirement to the road input data. Okay, and that's all my presentation, and thank you for your attention. And this is my personal website, where there's more detailed information regarding my research. Okay.
Okay, great. Thank you so much for the presentation. All right, so let's open the floor to the audience for any questions. Any questions from audience?
Yeah, maybe I could have one. Yeah. Hi, Dr. He. Nice presentation. Thank you. If time is allowed, I hope you can share some comments on how should we transfer the method used for traffic flow diagram to other similar time-space diagrams. I know many audience might not have expertise in traffic flow theory, or they might work on some other topics. But I believe your method has a great potential to be generalized to other time-space diagrams in different domains.
What do you mean other time-space diagram?
Maybe not time-space. You know, here time-space, we trying to measure the speed or density. I'm assuming in other domains, they have different metrics to represent. So I believe the key innovations here is trying to find the fundamental physics, say the wave speed, then you try to make some modifications to incorporate the physics knowledge here, then try to improve your method to representing the physics here, the metrics here. So I'm wondering, can you share some comments? How do you think we should use similar physics knowledge and incorporate into machine learning or other methods?
Sure. I would like to talk about how the idea come from. Okay, and that I think that's is kind of interesting because more than 10 years ago, almost everybody when I was a student, I know the time space diagram, and at that time, a lot of people we begin to collect high fidelity trajectory data, and then we found there's a we can see the traffic wave in detail, and then at that time we know the speed of the traffic wave is between -20 km/h and -10 km/h. And at that time, many researchers do something by using the new knowledge to revise the basic knowledge, the existing knowledge in the textbook. Like we know the wave speed, and then we revise the way to construct the fundamental diagram, okay? And we revise the way we estimate the propagation speed. Many researchers do a lot of things as they use the new knowledge about the traffic phenomenon to revise the traditional knowledge, okay? And then, so I have at that time, I think, what can I do? Like right now, a lot of people know the wave speed, and can I do something by make use of the knowledge to do some contribution to the traditional traffic flow theory, and then someday this kind of idea probably last in my mind for like several years, and someday I found the time space diagrams, and I saw, wow, the time space diagram look like in this page. This page, okay. The traditional one is quite obvious. The left hand side, traditional one is pointing down, but it's not consistent with the wave speed. Okay. So I roughly thought if I can do something to incorporate the wave speed into the very basic tools. Okay. That means after when we found some new phenomenon in the traffic, and we incorporate the new thing into the basic knowledge. That I think that, okay.
Oh, thanks for sharing those experiments.
May I jump in and ask for some clarification question? First of all, thank you, Dr. He, for the presentation. Wonderful, very open eye. So when you talk about the wave -10, -20, so while you're processing these images, do you dynamically select the wave based on the data, or how you handle the slope? Because you are doing this, NRP is based on the slope of the wave, right?
Yes. Fortunately, the wave speed is globally similar. I mean, no matter you are in the United States or in Europe, the wave speed is between -20 to -10. Okay, that make us we could select the slope between -20 to -10. And I also did a sensitivity analysis, and the result is now sensitive to the wave speed.
Oh, okay. So you're saying that it's a range, and you just randomly pick one number from the range, and you found out it's pretty robust as long as it's within 10 and 20, -10 and -20.
Yeah, and actually, the wave speed, like we take the right hand figure as an example, it can very consist. Each wave they have this very similar wave speed, and it will now change a lot. In this figure, we can see it's all about -16.
Okay. Sorry, but I probably didn't catch it. Is this for freeway, or is this for corridor or normal street, or doesn't matter what type of roads?
Oh, it's this work is for freeway.
For freeway. Okay, so when you can this method be used for regular streets with more intersections, with more other will the type of roads matter for implementing the method?
I think generally speaking, I believe it will work for the arterial, and because the basic is the logic is very simple. We just incorporate wave speed. As long as there's a wave speed, and the method could improve the traditional way, I believe. I believe the idea is, right here, this work, the idea is very straightforward, I believe.
Yeah,
And
the idea is very straightforward, and you also show the transferability. I was just asking about the generalization of the method.
okay.
Yeah. Okay. Can I ask for a little bit more details about the last part of your presentation, when you talk about using this to do the carbon dioxide emission estimation? You mentioned about macroscopic, microscopic. I think we're familiar with that. And so for this one, if you have time, can you give a little bit more detail about how to use this to calculate the carbon dioxide emission?
Use you mean my method or
Yeah, use your method.
My method is quite. I think the advantage of the proposed method is we can easily get the input data. Like for the
You mean the speed? Are you talking about the?
I mean for the we only need the time space diagram, a diagram like this, and then I can give you a corresponding carbon dioxide as emission. And but for this diagram is widely exist. And you can construct such a diagram using loop detector data, or you can also using floating car data.
Yeah, I understand, but you kind of describe a black box. I'm asking what is in the black box.
When doing the modeling, I also use some kind of a linear regression method. Like you mean did I model get the model?
How you go from this photo, this diagram, this image to the carbon dioxide emission level?
Okay. So right now we have 100% trajectory data, and then we have so you can see me. We have two hands, and for one hand we construct the corresponding time space diagram, and because we have the trajectory data, we can get the very accurate emission data, right? Because we have the vehicle-based emission estimation model. So for the two hands, this hand is diagram and this hand is emission, and we put them together and fit a model.
Okay.
And then
so you're using the learning.
Yeah, we
use the learning model to study this diagram, and then if you have new diagram, you can quickly find out what is the CO2 emission.
We surprisingly find the relationship between the traffic dynamic and the emission is quite simple. It's basically a linear relationship. And you mean when you talk about the transferability, we feed the model using the data collected from one freeway, and then we test the model using the data collected from another freeway. And that's I believe, and the results is quite convincing, and I believe, and the model has very good transferability.
Okay, great. Sorry, Dr. Zhou, I cut your question.
No,
if you have more, feel free.
No, I'm good. I think we don't have more time since Dr. He has a meeting at 1 p.m.
Just to see, how about the other audience? Any other questions? Last call. Yeah, sorry, today's seminar is a little bit short. We had some technical challenge at the beginning, and then Dr. He has a meeting at 1 and he has to leave a little bit early. But you know, Dr. Hao Zhou and also Christina has Dr. He's contact information. So if you have more questions, feel free to contact him. Okay. All right. Thank you so much, Dr. He, for joining us and give us this informative presentation.
Okay, thank you.
Thank you, Junbi.
Thank you.
Very informative. I learned a lot. Thank you. Appreciate it.
Thank you, everyone.
Have a nice weekend.
Yeah.
Nice weekend.
Bye.
Bye.